Our next speaker is going to be Paul Wooster. Okay. Paul Wooster is a founding member of the Mars Society, okay, and also led the effort at MIT and what we call TransLife, and they renamed the Mars Gravity Experiment, but is now the chief of Mars mission planning for SpaceX. So he's going to tell you about SpaceX's plans to send humans to Mars.
Yeah, thanks for the intro there, Bob. So I actually met Robert like almost exactly 20 years ago. I think it was in September of 1999. He was doing a book tour for, at that time, you know, his latest book was Entering Space. I had actually read The Case for Mars like a month earlier, went to you know, see his talk, and I was just like extremely inspired by the overall vision that he was laying out for expanding humanity into space, and why that's important, you know, really for humanity as a whole to energize us and help us move forward. So, you know, definitely a very memorable, you know, experience there. And then, you know, as he was saying, you know, did a lot of things while I was in college related to the Mars Society, really doing anything I could to try to make that vision reality, having, you know, people living on Mars. So want to definitely thank you for that, Robert. I have, you know, I will say I have heard him, you know, sing a few times before as well. Or maybe it was Boris, I don't know. So in terms of SpaceX was established with the goal of making life multiplanetary, to allow human civilization to move forward living on multiple planets. So in terms of what I'm going to talk about today, it's really focused on, you know, what is it going to take to make this happen? So that, you know, I met, you know, Robert, you know, and got involved in the Mars Society 20 years ago. Let's say, you know, in 20 years' time, can we have, you know, a Mars Society, you know, convention, you know, in a space like this, you know, on Mars? So in terms of what's going to be needed to make that happen, there's all sorts of things. I mean, if you look around, you know, here, you know, we're in, you know, basically downtown Los Angeles. You know, there's all sorts of different things involved in having a city, you know, be built and operated. And, you know, when we talk about cities on Mars, we're going to need all those same sorts of things as well. So, you know, it's something where, you know, we at SpaceX are very focused on the getting there part of the problem. But I really also encourage, you know, all of us to think about the broader set of capabilities that will be needed. You know, from, you know, food and you know, housing to you know, power and, you know, other utilities and so on, to make this sort of thing happen. Now on the SpaceX side, our focus is towards really reducing the cost of transporting cargo and people to places like Mars. We see that, you know, in order to have that vision be a reality, it has to be a very affordable, you know, there has to be a very affordable means of transport. So our focus towards that is to have a fully reusable transportation system. We've been making a lot of progress in regards to that with our Falcon 9 vehicle on the first stage, having the you know, first stage go up, accelerate the second stage up to a high energy condition, then having that first stage come back, land and be reused. We've been doing that, you know, quite a few times now. It's becoming, you know, almost you know, a regular occurrence at this point. Thank you. And we're you know, getting ready at this point to reuse one of those first stages for the fourth time, and we're going to be just increasing it from there. That said, to really enable something like this, we think that we need to decrease the cost even further. So for that, we're developing our next generation launch vehicle, which is basically the Starship. You can think of that, similar to the space shuttle as being the entire vehicle. Additionally, it's the second stage portion of the vehicle on top, and then our super heavy rocket that we have as the first stage to help accelerate that vehicle into space. So unlike Falcon 9, which is a partially reusable vehicle reusing the first stage, with Starship and Super Heavy, we're going to go to a fully reusable system. So we'll be reusing not only that first stage, but also the second stage. We see that as yeah. See that as being critical to decrease the cost, allow us to take very large amounts of cargo, beyond Earth. Additionally, in addition to being able to be fully reusable, we also need to have a pretty significant payload capability. You don't want to be, building, a city out of, small container size things. You want to be able to move, large cargo, large numbers of people. So we're developing the vehicle to effectively have 150-ton payload capability for launch into Earth orbit, and then by making use of propellant transfer, we can then take that same payload onto the surface of the Moon and Mars. That allows us to, really have a very low cost for delivery here, and combined with the fact that it's fully reusable, we'd actually expect that the marginal cost for a launch is actually less than the cost of launching a Falcon 9. So it's kind of this strange thing that I think people haven't fully grasped yet. But even though it has a very large payload capability, we expect just the cost per launch to be significantly lower than what's available now. As you increase your flight rate, it's important to have a propellant that's also relatively inexpensive. So methane is the least expensive fuel available here on Earth. So we're using methane oxygen on both stages of the vehicle. That also helps out from the standpoint of having a common engine and common propellant to really minimize the amount of development work you have to do, and even just things like the maintenance on your launch site and so on, by having that common propellant that can help you there. And then, of course, methane and oxygen are very useful when it comes to Mars in terms of being able to make them on the surface, and also behave well overall in terms of your ability to store them in space while still having quite good performance. I mentioned already the fact that we're using propellant transfer. That's what we use in order to basically take a two-stage fully reusable launch vehicle that's able to take a very large payload into low Earth orbit, and then effectively turn it into a three-stage, much larger vehicle to head out to basically higher energy destinations. So probably the most relevant for this group, obviously, is the surface of Mars, and something that can also support missions to the Moon and really elsewhere in the solar system. Of course, you have to be able to land, so that's a key focus of our development, as well as have a robust landing system that can land on a number of different locations. So not something that can just work on Earth or just work on Mars or just work on the Moon, but something that can cover that full spectrum of capabilities. And then in terms of this vehicle overall right now, it's something that we're moving forward with building and testing. In terms of what this all looks like for the Mars architecture, this is a picture. I'm actually going to come back to it a little bit later on, so you don't have to memorize all of it. So over on the left there, basically we use the booster and the ship, basically as that two-stage vehicle to get up into Earth orbit. We fill up the propellant tank, so we're basically leaving Earth orbit with a vehicle that's more or less has full tanks. We can then use that to go accelerate off to Mars. Can do a relatively fast transfer going there. 4 to 6 months would be pretty typical. and then uses the atmosphere to slow down and enter and land. For the return back, we would then make use of local resources, so water from the surface and carbon dioxide from the atmosphere to make our propellant to return back to Earth. We could then do a single stage return from the surface all the way back, again, using the atmosphere at Earth to help decelerate us, slow down and land. So that's the sort of overall architecture. This has been consistent for quite a while. We've been, I think, working in some depth on this for a little over four years, and this aspect of it has been quite stable. That said, we have been working a lot on all the details on the vehicle itself and what's involved in doing this in an efficient fashion. So I'll talk a little bit more about the status of that in a second here. So the first stage, what we call super heavy, is 9 meters in diameter. The entire vehicle is 9 meters in diameter. It's about 68 meters tall. It's drawing on a lot of the lessons we've learned from Falcon 9 reuse. So we have grid fins up at the top of the vehicle to help guide it back to the launch site. Landing legs, we've actually simplified that relative to Falcon 9 in terms of minimizing the complexity of the mechanisms there and allowing us to much more rapidly recycle the vehicle around. But if we'd gone back, I think 10 years ago and said we had a first stage with 31 or 37 engines, people would have thought, oh, that's impossible. Falcon Heavy, though, has 27 first stage engines, and in many ways the configuration here is actually even simpler for us than that. So I think we've again learned a lot through all the developments to date that are leading forward to getting this part of the vehicle flying. Now the emphasis on this is really just to at Earth get the second stage, the ship up to a high velocity condition such that it can then proceed onto orbit. But we don't really need this beyond Earth. It's really just to get out of the deep gravity well here. The part that's got a lot more new aspects to it from the standpoint of the overall functionality relative to what we've done to date is the Starship. So this vehicle is basically the second stage, but it combines the propulsion aspects of a second stage together with the payload elements of what would typically be in a fairing for launch of satellites, or something like the spacecraft for Dragon, and it's able to basically keep those elements together and go and serve as both a launch vehicle stage and an in-space vehicle. So that provides a lot of flexibility for those various maneuvers. Additionally, in order to be a fully reusable vehicle, this part of the system is also recoverable. So we're able to bring this back down to the surface of the Earth, go through entry, do our landing, and get it recycled around to fly again. This is all powered by our Raptor engines. For the ship, we have a set of sea level engines that we use for that landing, along with vacuum optimized engines that we use for the bulk of the impulse in space. And we can trade basically in terms of the effective specific impulse of the system versus the thrust level, just based upon where we are in our trajectories and what types of maneuvers we're looking to do. So a lot of good flexibility there that helps us have a very versatile system. This is a picture of 3 of those Raptor engines on one of our prototype vehicles. So these are basically what we call the landing engines. They're the three engines that we would use for a landing. We also use them during the ascent and for any high thrust maneuvers. To have the vehicle come back in through the atmosphere, we have to survive a very high heating environment. So that does require a heat shield as well. The approach that we're taking there is to, for one, have most of the vehicle actually able to withstand relatively high heat to begin with. So the primary structure of the vehicle is made out of stainless steel. That's been one of the changes over the past year that's really helped speed up the development of the system, get it flying, and it also has a number of benefits in terms of the overall system level of being able to withstand those high temperatures entry much better than aluminum or carbon fiber type of structure would, which then means you need less very high performance thermal protection material for it. That said, in the high heating areas, you do still need something that can withstand that extreme heating and be reusable. So for that, we're basically taking the lessons from the space shuttle program in terms of some of the things that they learned through the course of their activities there to make a much more robust ceramic, radiative and insulative thermal protection system. So we're basically building right now the capability to manufacture large quantities of that material, get it installed in a rapid fashion, and really cover up the aspects of that high heating for this vehicle. I mentioned the Raptor engine, already. This was this engine is a full flow methane oxygen stage combustion engine. We did a whole series of development tests with a smaller scale engine over the last several years. Basically, about half the thrust of the current engine. But earlier this year, we got the flight version of that Raptor onto the test stand. So this is a video of one of those firings. A little too loud, maybe. So, with the methane oxygen, you get this nice blue, clean flame. That's an aspect of the propellant combination that also helps out for reusability, having less soot build up in your engine. We've been doing a whole series of tests on these across different throttle levels. We've been up to 105% power, throttle them down for landing tests, things of that nature. We're also ramping up the overall production on these. We've, I think, had over 12 or so into testing at this point, and working to increase the production rate even further there. So in addition to the engine itself, one of the key elements is understanding how to build these large stages and understand the interaction between the engine and the stage. We're, again, trying to cut down the cost as much as possible, so we're actually using autogenous pressurization for the vehicle. So we're taking a portion of the oxygen that goes through the turbopump, gasifying that, sending that back up into the oxygen tank to pressurize that tank. Similarly, taking a portion of the methane up to high pressure and sending that back into the tank. And that allows us to get rid of helium as a pressurant on the vehicle. Helium is actually quite expensive. It's particularly in the quantities that you would want for this type of vehicle. That's something where being able to instead just use the quite low cost and high density storage from the cryogenic propellants can help us out there. And that also, again, helps when we're looking at Mars and things like that. There's not a very readily available source of helium there. So being able to instead use your own propellants for pressurization helps out. That said, that's one of the things that we've been looking to do is understand the interaction there between the engine and the propulsion stage, along with how the overall tanks get built and work out there. So we've been doing a series of tests with our Star Hopper vehicle. So here's basically the final flight of that vehicle in August of this year. So yeah, that vehicle is 9 meters in diameter. Nice clear flame. So yeah, so that's the full diameter of the Starship. It's basically the somewhat shorter version of the propulsion tank from the vehicle. yeah, there's no one on that. There is a silhouette of a person painted on it for scale, but. Thanks. So this was at our Texas, our South Texas test facility, what we call Boca Chica. It's basically as far south as you can go in Texas and still be in Texas. You know, like at the very edge of that view is basically the Mexican border. So this area is, you know, right by the Gulf of Mexico there. Have been building up this site. You know, really basically over the last year or so to be able to do this testing along with manufacturing the vehicles themselves there. So we have this facility down in Boca Chica near Brownsville, Texas, and then in parallel we're also building vehicles at the Cape. So over on the left is the next prototype vehicle, what we're calling Mark I. In this case, it's the full-scale vehicle, all the aerodynamic surfaces and everything else that we need for that we built in Boca Chica. And then the picture on the right is a picture from Florida. And we have another vehicle, you know, maybe harder to see in the picture there, but you know, the main tanks and such in the background, most of the nose cone in the front, and then the very tip of the nose cone over on the left. All coming together in Florida, and then also a lot of barrel sections there for the next vehicle after that. We're really trying to speed up the pace of development on this and overall spur innovation by having two sites that are in a friendly competition to you know, drive forward, get the vehicles built and flying and into testing such that we can learn as much as we can, as quickly as we can, and to do that all in a, you know, collegial fashion where we're sharing lessons learned across the sites. They're, you know, in constant communication, but they get to set their own path in terms of what's going to be fastest to get the vehicle built. And I think we've already seen a lot of very good improvements there in terms of, you know, one place trying out something that's a little different from another, seeing that worked really well, and then the other site picking up a similar approach. So for this vehicle here, what we're going to be testing out with that is basically the overall landing sequence for this vehicle. The vehicle flies basically in a sort of side-on condition through, you know, subsonic flight, maximizing the drag area on it. One sec. So, there we go. So cute. So basically in hypersonic and supersonic, we're flying about 60 degrees to the flow. That's letting us maximize the drag to slow us down as much as possible while also still having sufficient lift to control the trajectory as it enters in to basically manage the overall heat that the vehicle is seeing on that heat shield. As it comes, so it's more or less flying, you know, horizontal through most of the entry. As it then comes towards subsonic and sort of terminal condition, it's almost falling, you know, vertically side onto the flow. That's letting us really use as much of this area as possible for drag, keeping the velocity that we need to, you know, remove with the engines as low as possible. And then we're using a fairly non-conventional approach of basically modulating the forward flaps and the rear flaps, almost more like what a skydiver would do to control their trajectory coming in, to adjust for any wind disturbances and so on, such that we can target the landing site and arrive there. So in terms of what that will look like, this is an example of the subsonic flight there. You can see the forward and aft flaps actuating. They're actuated along a line fairly close to parallel to the vehicle. Again, these basically are not really wings or flaps in the traditional sense of something creating lift. They're more actually modulating drag than that, and then able to provide some side force based on the normal force against the flap. This can guide the vehicle in. You can see it's going at a pretty low velocity there. And then for the final portion of flight, we basically have to do a reorientation maneuver now to bring the engines first and do the final propulsive landing. So this is what we're going to be testing out with that prototype vehicle that you saw the picture of there. So this is basically a simulation of what that's going to look like. This is our trajectory, simulation code, and then visualization layer on top. I'll show that again. I think people liked it. So, not too distant, future, next, few weeks, we'll be getting this vehicle here out to the pad, getting it through its static fire tests, and then, hopefully, doing making that animation reality. And I'm very excited about that. Really looking forward to it. That said, we are taking an iterative approach where we're expecting, to learn a lot as we go, and we're moving fast. So, if that vehicle, has some issue, the next vehicle is going to be, right after that, and the next one right after that. Our approach is really to test a lot, fly a lot, learn quickly and adjust as we go forward. I think the flap size is all based on just what's needed to control the vehicle, have enough modulation to the lift on the vehicle to basically adjust from wind disturbances and so on. It's really driven primarily by the Earth case over, say, the Mars case. There's different trades there, but we're basically able to use those same aero surfaces in both locations. So after we've basically been testing out these suborbital vehicles, next step after that's going to be orbit. So to give you a sense of scale for that, that same Hopper vehicle you saw earlier is over on the left. There's the silhouette of the person and some real people. And this is what the launch pad looks like. And then the vehicle itself. It's super heavy. And then the Starship all the way to the top. So again, that's a depiction of what that would look like in Boca Chica, Texas. We're also building out a launch capability in Florida as well. This is now a depiction of how the overall vehicle would operate. So basically the first stage would accelerate that second stage up to high velocity. We would do stage separation, and then the first stage is super heavy. Would turn around to do a boost back burn to come back to the launch site. In order to do very rapid reuse, we want to be bringing that first stage back as quickly as we can. With Falcon 9, a lot of times they go downrange on a drone ship, but as much as possible, we want to be bringing these back so we can turn them around quickly. As that comes into land, the second stage of the ship would continue onto orbit, and then one of the key things basically beyond that full reuse that we're looking for is the ability to do propellant transfer. So having taken on that propellant, we're now ready to really go on to pretty much any destination. It's actually less delta V to go from low Earth orbit to the surface of Mars or the surface of the moon than it is, being used to get to orbit to begin with. So having reset that overall propellant state can really help us with all sorts of different mission types. In terms of how we do that propellant transfer, this is something where there's been a long list of things that have never been done that are involved in this overall architecture working. So, first stage reuse is definitely a big part of that. Operating a vehicle with very large numbers of engines is another one. But those have been done. Recovering the second stage from orbit is definitely another one where Space Shuttle has a lot of experience there, but being able to do that in a very mass efficient fashion and being able to rapidly reuse that system is a critical ability. And then large scale propellant transfer on orbit, particularly using cryogenics. So the Russians do actually a fair amount of propellant transfer. That's all not been cryogenic though, on a much smaller scale. So we're really looking to scale that up with this vehicle. So our approach there is that we are actively settling the vehicle. That allows us to avoid some of the sort of fluid dynamics and slosh and so on that you might otherwise have to deal with if you were trying to transfer in true microgravity. So we use a small thrust to settle the propellant down, and then differential pressure to shift the propellant from one vehicle over into the other. This is somewhat of a brute force approach, but through the architecture as a whole, I think we're able to leverage the very significant capabilities of it to simplify the rest of the developments that are needed in order to go and get to Mars and enable all these things we want to have happen. So this is something we'll be looking forward to proving out in the near future as well. So all of that, coming back to this chart, is sort of highlighting some of the key elements that we'll need to make this happen. And beyond just going and landing on Mars, the system also opens up capabilities, for example, to deliver very large payloads to the moon, set up and operate lunar bases. And because it's the same system that's being used for going to the moon and going to Mars, it's not something where you have to stop going to the moon in order to go to Mars, or it does not need to be something where it needs to be an either-or type of proposition. We can only go to the moon or we can only go to Mars. We're really excited about the possibilities of doing both, having bases on the moon while we're also setting up these cities on Mars. Thank you. Thank you. Go ahead.
Okay. So, without revealing any trade secrets, can you tell us the sorts of differences between Mark 1 and Mark 2, Boca Chica versus Florida, and also how many Gs is it going to be coming in? Are there things that you can do to reduce those when you eventually go to Earth at some time in the future?
Yeah, so there were a couple of questions. One was about the difference between the builds at Boca Chica versus the Cape, and another one was about entry dynamics. The vehicles are quite similar between the Cape and Boca. There's some differences in the thickness of the material. Between the first two, we're basically, as we learn, we're able to thin some of that down, decrease the mass. There's other things on the manufacturing side, but a lot of the capabilities are basically the same there, and it's more just a matter of refining things. As we get into the next version after that, we're going to be making more improvements to decrease the manufacturing time and cost, and just help out with the overall operability of those vehicles. In terms of the entry accelerations, they're actually pretty benign. For entry from orbit at Earth, you're less than 3 Gs or 2 to 3 Gs. There are some things that could be done to decrease that more in the future as well, but relative to some like capsule type reentries and so on, that's relatively benign. And then for Mars, for the entry there, we basically have a trade between how much acceleration you can take versus what entry velocity you can come in at for an aero capture. But we're able to basically limit ourselves to 5 Gs, which is basically the limit for a deconditioned crew that NASA holds. So we can limit ourselves to 5 Gs and still meet those fast transit times that I was talking about. Sure.
So from a single stage Mars to Earth, is it direct entry into the atmosphere or some other way of? And then my second question is, the first ISRU of propellant on Mars, is it going to be robotic, or will you just leave the starships there and wait for humans to do the
Okay, so the questions in general were about returning from Mars. For the single stage from Mars back to Earth, you basically would be propulsive departing Mars, do trans-Earth injection, and then you would use the atmosphere, most likely to first aero capture into Earth orbit, and then subsequently do your entry and landing. That said, there's a fair amount of operational flexibility on the system there. In terms of what we would be doing early on, I would expect that most of the vehicles would actually stay on Mars. They'll be quite valuable there, and vehicles returning would be more to the extent people want to come back, they would be coming back in a vehicle. But at least early on, most of the ships I think would be stay there and be made use of on the surface.
So SpaceX is moving pretty fast. What if there is not enough systems developed to put inside the Starship? Like, do you plan to set up something yourself, or?
I don't know, are there things you're working on? I mean, I think there's going to be all sorts of things that will be needed to have a city on Mars, and at SpaceX we're very focused on enabling that by having a robust and low-cost transportation system that's going to be available, and we really want to encourage anyone who wants to be working on the things that will be on Mars to do so, and to think about what things match up well with your expertise, or things that you want to go learn how to do, and then build the things that can fly there, figure out what all the different businesses will be on the surface of Mars. We talked about, like, probably want to have more than one pizzeria or something like that. I think that from the SpaceX perspective, we're quite interested in enabling that type of activity. If there are certain things that are missing and we need to help out there, I'm sure we'll do that with time. But as much as possible, we'd like to foster an ecosystem there.
A comment and a question. You do realize that Heinlein got there 70 years ago with his book, The Man Who Sold the Moon. And the question is, those grid fins, are they actually sort of like waffle irons?
Yeah, so the grid fins on the first stage for both Falcon and Super Heavy, on launch, they're kind of against the side of the vehicle, but then they deploy out for entry. And so in that case, they are actually creating lift, but you can think of it as a whole series of small wings inside there that are, as you rotate it, each one of them can create lift and thus generate a side force for the vehicle. So the air passes through it.
Can you comment on whether there are any special issues from firing over 30 engines simultaneously on the Super Heavy as far as turbulence and stability and so forth, and how those have been addressed?
So in terms of firing a large number of engines, there were, I think, a lot of questions. They came up, I think, even back when SpaceX was talking about a Falcon 5, people were worried about the dynamics of that, and then Falcon 9, how is that going to work? And Falcon Heavy with 27 engines. The step to the number of engines on this is not something where I see it as having a significant issue there. It's more just incremental in terms of acoustic energy and so on, but not anything that's fundamentally showstopper.
Hi, Paul. I'm from City, China, and my question is Donald Trump said we'll send American people to Mars by 2033, right? So I want to know what is the plan? Is till 2024 or other time for your plan, for Elon's plan? And second is Elon said we'll send 1 million people to Mars, right? So how we can block the seats now?
Didn't quite hear the last bit of the last question.
Last question is how to block the seats for Starship to Mars.
Oh, book. Oh, okay. Book. Yes, sorry. The reservations. So we're not yet taking reservations, but if people are interested, definitely let us know. On the question of overall timelines for this, we're looking to get the vehicle into orbit. That's the first thing that we'll be doing in the next basically within the next year, and putting a lot of effort into that. From there, we'll be doing things like the propellant transfer and so on. In the past, we've talked about sending cargo missions to Mars in 2022, and that's still very much on the table. And then based on the overall sequence, being able to send crew missions in the next opportunity after that. The opportunities going to Mars are about every 26 months. You'll want to put some significant supplies and infrastructure and so on in place to support the first crew. You want to make sure all that's working before you actually send them. But I don't think there's anything that's precluding that.
So I was just wondering if you could talk about environmental control and life support systems, like what version of the Starship they might go in, and kind of any changes you have to make from standard configurations for the long trip to Mars.
Yeah, so the Starship has a number of different configurations, some deploying satellites, some carrying cargo, and then obviously some carrying people. Early on, you would tend to have a relatively small number of people with a lot of cargo on any given ship, and then with time we would go to have significantly more people, and then depending upon the mission, you'll have a duration there. So for say a relatively short duration with a relatively small crew, such as what you might have for flying around the Earth or going around the moon and so on, you could use technology that's fairly similar to what we're using on our Crew Dragon right now. That said, when you want to go to Mars, you're going to want to do something that's significantly better than that. That said, when you have a relatively small crew size, the technologies that have been employed on the space station and a lot of the work that NASA's been doing, really can be sufficient for this type of mission, given that we can also make use of a lot of basic mass to carry extra consumables, spare parts, and so on. So I don't see that as necessarily being a showstopper. It is an area, though, that does need attention, and it's an area where, as more capabilities come online there, you can basically increase the efficiency of your system. But early on, mass cures a lot of sins.
So one question and one hope. Given the previous designs were supposed to have about 1,000 reuses for the booster and 100 reuses for the tankers, and given steel's better fatigue properties to aluminium, has the change to steel improved the reuse of the boosters? And Any chance of you guys coming down to Australia and building these down there? I mean, we're close to the equator and we've got a really good steel industry, so we'd be happy to build a bunch of them for you if you want.
All right, thanks. Yeah, we are looking for the vehicle to be highly reusable and rapidly reusable. I think early on it's going to be more that we'll be rolling in upgrades and so on, probably before you necessarily are running out of life in some of these vehicles. So we'll just see with time. But yeah, some of those numbers you were quoting I think are from 3 years ago or something like that. And those were sort of some thoughts at the time. But I would imagine eventually those will be even better. And then certainly with time getting point-to-point transport on Earth, including to back and forth to Australia can definitely make the world a lot closer together.
Hi, Paul. A couple questions. So I noticed that the dry mass of the Starship has gone up a little bit from 85 to 105 tons, but also the payload capacity now seems to really be firm at 150. So that's great news. I'd love to hear sort of what maybe is behind that. And then my just second follow-up question is, are you guys planning to publish a revised economic estimate anytime soon? Because the only thing out there, I think, is from Elon's 2016 talk.
Yeah, so I think in the progression, so there's sort of been, it's now becoming a tradition almost of having an annual, talk in around September or so. So back the first of those, which was in 2016, Elon laid out the sort of the overall vision of things and what would be needed to make life multiplanetary, established cities on Mars. Since then, we've more or less been working within that same framework and developing a lot more detail on the vehicle itself and sort of sizing it to at least initially be somewhat smaller maybe than what we had been thinking for the longer term there. But I don't think there's anything particularly surprisingly different about the overall economics of it. We're still targeting it to be something that as we build up with experience with it, where large numbers of people can go. Really want to enable that.
We'll take a couple more questions.
Hello, I am a student from Poland, and I have a question about the trajectory, because we saw the simulation, and I'm really curious about how much deceleration you get from aerodynamics from the atmosphere, and how much you get from the rocket fuel, and at what height on Mars you change your position, because on the simulation it wasn't so clear. And also on the moon, you do not have any atmosphere, so you would have different type of movement, I suppose. And the last question is about radiation protection. If you could get into detail a little bit.
Yeah, so on the trajectory side, the vehicle's basically designed to be able to land at the Earth, Moon, and Mars. Depending on which of those specific cases, the ratio of energy dissipated aerodynamically versus propulsively is obviously quite different. In the case of the moon, it's entirely propulsive. In the case of the Earth, over 99.9% of the energy is removed aerodynamically. There's this saying that at Mars the atmosphere is thick enough to be a problem but too thin to help you. I don't think that's actually true, in the sense that over 99% of the energy is being removed aerodynamically at Mars. So there is an animation actually up on our website at spacex.com/Mars that shows the Mars entry trajectory. It's shown with an older OML, but the trajectory is basically the same. And so in that case, we're coming in at 7.5 kilometers per second, slowing down to 750 meters per second or less, and using that to really bleed off a lot of that energy. For radiation, for the interior cabin layout, we basically have, when we're sending a large number of people somewhere, there's both individual cabins and then large common space, and then we basically have sort of a central column that can serve as a radiation shelter basically very similar to the original Mars Direct types of things of using your consumables and waste products and so on as additional shielding, such that if there were a solar particle event, you can go in and take shelter there.
These will be the last 3 questions.
Hi, Paul. So you said that the tanks are going to be autogenously pressurized instead of helium pressurized. How do you start the engines and the turbopump, especially when you're at low tank pressure?
Yeah, so there's basically, the engines, as I said, are pressurizing the tanks using autogenous pressurization. We're also able to basically spin the engines up, with high pressure gas, and then can recharge the high pressure gas as we go.
Hi, Paul. Can you tell us a little bit about the reuse of the heat shield and how often that might need to be refurbished?
Yeah, so the target there is a very low required maintenance, and we think we have a good approach to that. That said, we're going to see how it goes as we fly, and we'll take that iterative approach to adjust as we go. But we're not going to be locked into one thing that we have to fly forever. We'll adjust as needed.
Hello, I'm interested in the sort of abort to launch, abort to orbit options. Is it similar to the pusher system you're developing for the Dragon 2? And what sort of design challenges do you have for saving such a large second stage?
Yeah, so the vehicle is, as I said, quite large. Depending on if you had a particular issue at different phases of flight, you might do various contingency trajectories, including things like abort to orbit. You can actually take, depending on where exactly you're headed, you might end up wanting to reserve a lot of propellant margin for those types of issues, but that's not actually really a waste from the standpoint if you had to take on more propellant after you get to orbit. That's you need that propellant anyways. The other thing that we're going to be looking to do is really across the board have a very fault-tolerant vehicle and highly reliable vehicle, which we're really going to prove out through a lot of flights. Having that full reuse means that we can fly the vehicle, many times to ensure that it's something that's going to be good to fly on.
My question probably a little bit similar to what we just heard, but the point is, once the Starship enters the atmosphere at a high speed, 8 kilometers a second or probably 11 kilometers a second from interplanetary space, it's subject to huge heat up. Do you have any technical solutions inside the Starship body which will help dissipate this heat?
So the question was about the heat rate on the vehicle, what temperatures you get to. So the exterior of the heat shield can get to very high temperatures. That said, almost all of that is radiated away, from the heat shield material, and it's insulative such that the back side of it is not getting as hot. And then for example, at Earth, as you're then descending back down through the atmosphere actually ends up cooling off the tile as well, such that by the time you're landing, it's no longer super hot.
So it's purely irradiation.
For Earth entries, it's radiatively cooled. Basically it radiates off. For higher velocity entries, you might like coming back from Mars, do some ablative in that case. But the need to be super fully reusable is less important for that sense.
Nice to see the results.
This will be the last question.
Thank you. If you're going to be doing faster than Oman transfers to Mars, will this widen the launch window to something less than 26 months?
So when you have sort of this ramp up in delta V capability, that does mean that you can launch more frequently than you might otherwise. That said, there'll still be, if you want to go as fast as possible for a given delta V, that tends to have a pretty narrow window. You can also open up things like Venus flybys and so on, but I think that's going to be something where we'll see, how much, if at all, that's actually useful. There are some cases where you can launch earlier, but you arrive later, which is probably not actually going to be all that helpful either. Yeah, there are some strategies once you have a very large fleet where you may want to be doing some of those types of things, just in terms of pairing up, departure and arrival times, and then the next departure. But I'd say that's maybe a little further down the road.
Thank you.
All right. Thank you. Do we get to keep the model? Okay.